Hello everyone. My name is Yuhong Lee, and today I gonna introduce this project Medusa. Just uploaded to ICML YouTube recording. So in this recording, I'll just discuss how all this project works in a very detailed way. So first, let's see some demo. Okay. This is Medusa incorporated with Vicuna 7B. We can see here this one for Vicuna 7B is a greedy sampling, so they're pretty consistent output, same input, same output, faster, way more faster than the one without Medusa. This is the Hugging with Face base implementation. And this is one with the optimized Medusa code. And so for all the thing, all the stories we go down to the observation. Why we need the Medusa? Okay, so when we look at the inference price, output tokens are always usually 2x more expensive than the input tokens. So for the chatbot we have a bot. Okay, the bot input is the user's instruction prompt. You can code it whatever you want. Just say prompt, okay. And the chatbot will say something like I, and then go to the next, and a chatbot, okay. Bot. So this is the prompt price. This is the whole thing's price per token. It's a screenshot from, I think it's from last year's Twitter. I'm not sure how this changed. Maybe this price will drop, but it's still more expensive than the output than the input. But this might drop this year because of the optimization implemented. Okay. But why? Why? So the reason is for the inference, which is generation, one by one generation, follows a memory bound computational pattern. The memory bound, specifically memory bandwidth bound. So which means we are loading for example, if we do a matrix multiplication, A multiplied with B and you get C, right? So the computation can be very fast because your computer is very good, which is like you have a very high flops, right? But you have a very large matrix and you need to transfer it from the HBM to the chip. But when you transfer this waste to the chip, which is where the computation happens, the chip. Let's draw a calculator here. Chip computation might be very fast, but what you are using is a very narrow bandwidth to transfer the weights. So this latency could be higher than this one, right? So the bottleneck will become transferring the weights because we are computing just one token. So the computation is pretty fast, but the weights transfer way more slower than computing. Okay, let's go to the next. Yep, the sequence shows the nature of autoregressive decoding. As we mentioned, each time decode one token by one token by one token. and underutilized arithmetic computation capability of the modern accelerator. By the way, at the end of the slides, I will just show you some appendix in the paper, and we have the very detailed discussion of how these things works, like how what we observed and how we can like build uh like the estimator of the model just to predict like how these models how like how this all these speed latency stuff can work, you know. And there are some existing works which we call speculative decoding. They use a very small draft model to generate several tokens at each decoding step. Because a small draft model, they are basically they are very fast, or they are computational bound, not memory bandwidth bound. And they're fast, and we just use their outputs as a gas gas token and feed that to the large language model. Use a large language model to verify. And we hope that just more than one token get accepted, which means the performance might be faster. Like it might be better than just originally like use a native LLM to do the decoding. Okay, we go to one example. So a prompt for Vicuna, we have this. This is a format, but just feed all the things into the model because we have the user's words, like you typing on some instruction queries to the element. Press enter, and we'll see here the context can be processed just one time. It's computation bound. Okay, because we are processing the whole things to the LLM. So computational bound. And for decoding, you can see here we decode words one by one. Once first we decode once, and then we put once, like we decode once because the last one is once. Okay, decode once, feed into the this is the LLM, feed it feed it into again and output upon yada yada at time. So this is memory bound. Okay. And we'll talk about the equilibrium in models output. So in this example, we basically we are using the what we call is a greedy sampling. So for models has a one, this is LLM output. For example, if we have this all this prompt here and feed once into the model, once into the model. The output is let's say if the vocab size is 32,000, then we will choose the outcome is the argmax of the output, which is like the one with the highest probability among the all the vocabulary in the output logics. Okay, so we choose outcome, and we can see here we have the outcome and then have a time. We shift all the thing because we have this sampling scheme, greedy sampling scheme. We shift that to the right, and they matches the input. Basically, they matches the input. And if we change a sampling scheme, it could be a little bit complex, but right now we just use a greedy sampling. However, you can see for a prompt here, there's no equilibrium. Basically means when we shift, the things shift to the right side. You see this matches, but this not. This not. Why? Because the whole these things are not the model's input. So only the models itself generated words can follow these autoregressive equilibrium patterns. So let's see what if we change the village to the mountain. You can see here we modify the village to the mountain. The mountain's output is still village, but what's supposed to be out? It's supposed to be a village nestled in. So this not matches this one. In a greedy sampling style, this doesn't match this one. So which means that mountain be modified. And later the rest of the outputs they're not consistent. Right? This not consistent. This matches, but this not matches. So what can we do here? If we interpret it from another perspective, we can see another very interesting thing, which is suppose we have a very strong small model, which we call SLM, very small model. So it generate these tokens faster, like 10 times faster than a large language model. And we put them together into a large language model. And we use the large language model as a verifier. So we verify if the model's output shift to the one right shift matches the input. This matches this one, good. Matches. This doesn't matches here, right? Mountain doesn't matches the village, which means the small model predict the mountain is wrong. Okay, only predict 3, 4, 5, 6, 7. They only predict 7 tokens, 7 correct guessing tokens. And it leads to 8 accepted tokens. However, so let's see. We feed once into the small model. Let me change the style. Okay, into a small model, and small model generate this, 3, 4, 5, 6, 7 tokens. They are correct. And we have 8 accepted tokens because small, we have this verification verified small. This one matches the right shift of the model's original output. Small matches the output. So village can also be accepted because if we do it in autoregressive, we still need to put a small back to the large language model again, and the output must be the village, right? So it's 8 accepted tokens. And you will see here, but default decoding, we only have the upon being decoded. But right now we have upon a time, comma in a small village, 8 tokens compared to 1 token. This is just a very abstract illustration of how a speculative decoding, parallel decoding works. And for Medusa, basically we instead of introducing an additional draft model, we directly add multiple heads on top of existing model to predict subsequent tokens. Yeah, so there are some benefits of the Medusa. So the key components is Medusa has, and we'll introduce tree attention and the training recipe and extensions. So here, a very simplified Medusa pipeline. So basically, Medusa has for example, if we have a large language model, we have this language model head. This head predict the next token, and this Medusa has predict the next. This one predict the one after this one, predict the one after this one. So right now we can predict 3 tokens ahead of the original tokens. And for Medusa has is pretty simple. We have 3 different heads, basically 3 different heads. Each head has this rest block, and one linear block. When we initialize it, we copy the LLM hash width to here, and we can do the initialization for basically for rest block, make them like input consistent input and output, which the input and output can be initialized as the same, right? Because we can manipulate it, like make it a linear 0 or 0, and it's a rest block. So you have a residue map from input to the output. So it should be the same. Okay, and then we do the training for this. For training, it just do right shift. For example, if you have let's say if you have input tokens and LLM, you train the LLM tokens is you shift the input token, right? You use this one for the LLM. For example, this is 1, this is 0. Use 1 matches the zero's output and calculate the loss, right? Calculate the loss. But for the Medusa head 1 is in the Medusa head 0, try to predict the second one. So you put 2 here. So for example, if you have the Medusa, this we call it 1. This is the LM head. This is Medusa 1. Okay. You compare it with the second one, third one. For Medusa head 2, you compare with the third token. Okay. And then trend tokens. It's quite messy. But I think you get it. A very simple training strategy. And let's talk about inference. So we have a models has. So this is the original one. We already has the prompt. It's just exactly the same example from the previous slides. We have the models has once, Medusa has upon. So we have the first. This must be the model's next token because the model's original has output is once, and we also has 4 output from the 4 Medusa has upon Lee and time the comment. What we do here is we concatenate, concatenate them and feed into the large language model again. Once upon Lee time and comma. So we have this right shift. Remember that right shift upon matches the upon. Okay. This doesn't matches the ly. This doesn't matches the ly. So we stop here because once it's the model's output, remember I will just iterate it again, and you feed the model's autoregressive result into the model, and the must be the model's output in a greedy sampling way, right? You feed the model's autoregressive output into the model's input equals to you concatenate them together and feed into the model, and they must be accepted. However, for default decoding, we only accept it. What about next one? Next, we can choose the some we also have the Medusa has tokens here, predict token here. So like the model right now, you can see from a second dimension. So this is the model's output, but you can see from a second dimension, let's say this is Z dimension. You also have the four Medusa has output here, right? Four Medusa has output, kind of abstract, but for example, if you have once a comma in here, you have the Medusa has one, Medusa has two, Medusa has three, Medusa has fourth output here. So we stop here. This is we have the three, like four different Medusa has output here through this dimension, right? And that's time, comma, there. So we put them together and feed into a model again. So now we can see time matches time, comma matches comma. These two doesn't match at all. So we stop here. Remember what we say? If this matches this one, which means this is the model's autoregressive output, you feed it into the model again equals to concatenate and feed into model together. And the output is model's output is in. So three tokens decoded. Compared to the default decoding, it only decode once upon right now we decode uh upon time comma in, right? So yep, so more tokens being decoded with two decoding phases, right? We decoded five tokens, total five tokens compared to only two tokens, so it's 2.5x acceleration rate. And let's talk about something more complex. It's called tree attention. Because for the Medusa heads, sometimes the top K prediction in each has also makes sense, right? So for example, this is the LLM's output. This is Medusa has the first Medusa has output. So the top three might be, for example, if this output is it, and it might be prime is or can. So you can see three or even four, or it could. This all makes sense, right? The prime is can could also make sense. So we want to include more possibilities into the path. So in the previous examples, we use a chain, which means each time we only include the top one Medusa has output into the calculation. But right now we want to utilize like top K, right? So that means we will introduce a tree. How to fully utilize. So our solution is for each head. We have this head one, head two, head one, for example, here, head one choose like top two, head one, two choose the top three. And what we do is we do a combination of this. So there are six combinations because 2 times 3 equals 6. And in it can be reflected from the attention map, feature maps. So this, so we have six combinations, but on the attention maps, we just flat this tree. You can see we can flat this tree. and use the attention map to like to indicate the relationship between the parents and the children. So for head 2, we have this is the if you don't know the attention like mask, you can just refer to some attention explanation videos. I don't want to explain this here, sorry. So we have this is, and is has this attention with the it. And for a prime, it also has the attention with it, but it doesn't have any attention with this one, which means this is a negative infinity. Okay, and for the you can see only all the children only associate with uh its parents or its ancestors, right? Yep. So basically, if we have the like top 2 plus the top 3, then we have this is like the total tokens, like additional tokens we need to add is like 2 plus 2 times 3. Okay, and there are 8 tokens we need to add here. Do we create this map? So this is for constructing a top 2, top 3 trees. And how do we do the verification? It's kind of very similar to the one we used in the trend example, which is previous example, but we just change that in a tree style. Okay. In this example, each number represents a unique token. So we have so this is like top 3 and top 3 tree, right? So we have like, I just give you a very detailed explanation here. We have the query, we have the prefix and key, prefix and the tree attention. This is tree attention. How do we do that in this scenario? Okay, we'll see here is basically for a tree attention, all the things will associate with its past tokens, like its ancestors. So for example, 3 here, there's 3 on the mask. See 397. This is the 3 mentioned here. Only associate with 2, right? With 2 and with 5. And also associated with all these previous tokens, which is a prefix. A prefix. So yeah, so that's what we do. And go to the next slides. How do we do the verification? So for is kind of like we use a right shift to compare each layer of tree with a generated tree. So because 5 is the LM has alpha, so feed into the LM and 8. We have this 8. 8 must be the LM's output in autoregressive way. And we'll try to find if there's any 8 in the Medusa head prediction. Okay, we found one. We found 8 here, right? So then we'll see the 8. We go to the LM, the output is 7. So we will continue to find if there's any 7 in the age children. Okay, we found 1 7 in the age children. It's kind of like DFS, but it's not the DFS. It's a verification. we can see we have this path being accepted. But if you, let's say, if you just ignore all these things, ignore all these, so it's literally a chain, right? It's literally a chain, and we do a verification. It's like 5 and 8 and 7. That's the input to the LLM, and the output is 8, 7, 0, right? When we do the shift, we see this being accepted, this being accepted, see, right? And also 0 must be accepted. So it's just like a complex version of the previous chain example. And then we can create a new tree from 0, because for each LL has, there are always Medusa has a comment, create a new tree. So can we parallelize this one? Okay. We can use a partition representation of the tree and convert it to table by indices. Right? So we have 5, 5, 5, 5, 5, 5, and 8, 2, 1, and 7, 3, 9, 7, 3, 9, 7. We also have this one. So this is like a real tensor we used in the computation. We do the shift and compare. So for like you shift them and you can see, okay, all these 8 matches this 8. And we try to find the maximum path here. So because these two being accepted and this is not. So this is the maximum path we can accept it, which is like, so that we have 3 tokens accepted here. So yeah, it reflects on a real tree, like on a tree, it's just like A7 and 0 being accepted. And yeah, so in the previous slides we talked about tree, but there's no free lunch, right? There's no free lunch in real application because we added more like nodes on the trees. We need more computation. And for example, if the computation it's like the there are 2 terms. One is the acceleration rate and divided by the latency, right? That's a speed up, right? That's that's a speed up. This is like sorry, that's a real speed. However, when we add more candidates to the tree, latency will drastically increase. So you can see here, even though our acceleration rate, which is like how many tokens, average tokens we can decode in one inference, slightly increase in a logarithm manner, but because the latency just increased drastically, so total speed drops. In our experiments, we found out that numbers of candidate tokens around 64. This is a best for models only 100. But for different hardware, though, there are different numbers. These should be configured and explored. It's like hyperparameters. And also here we have this sparsity tension, which means it's easy to understand. We'll just explain that in the next slides. So the sparsity It's kind of like we can prune the tree and make it like left tilted, right? So for example, if we have like 0.1 for most right tokens, and this is also 0.01, and this is 0.001. Why we need these nodes on the tree? Because this will never be accepted. You times them out. You don't need to waste the resources to calculate these nodes because the possibility like we have to get it like these nodes being accepted is so low. Like so we just prune the way. And when we do benchmarking of this one is basically we just calculate the expectation of each nodes on a certain data set. For example, we go through like the whole data set has like 10,000 tokens. We just see like how many tokens this one can hit and how many tokens this one can hit, right? If the total generated is like 10,000, we just see like if this can hit like 1,000 or this can hit like 900 and this like 100 and this is for this one is so low it's like 6 or like this just one they get removed, right? So it's just based on statistical calculation. Yeah, very simple way to create optimized tree. And once a tree is created, we make it static. So we 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 configure this tree and don't change it during the inference. Only use them as a statistic uh way to for inference. And then we can go back to the previous slides. You can see sparse tree is much higher acceleration rate compared to dense one because it just removes some underutilized uh, nodes on the tree. So we introduce another thing called Medusa 2. The key motivation is we can just instead of just fine tuning Medusa hat, we can just fine tuning the whole model with this hats and then can gain more acceleration rate. So how to maintain the performance of the models? So yeah, just first we have trained it use Medusa 1 recipe and then use smaller learning rate. For example, we can use the 2 Aura for training efficiency for like larger model, like 33B or something model with that size of weights. Yeah, and basically there are some comparisons here, just numbers in the paper. You can just read it. I don't want to explain this one. And the models without fine-tuning data. So this is kind of interesting because for a lot of models, open source, they don't have like the models can use like RLHF or like soft fine like what I call is soft fine tuning, right? Supervised fine tuning, sorry. And DPO, PPO, whatever. Like a lot of different strategies, and we don't know what data they use for fine-tuning these models. Yeah, our approach is we can slightly change them. Like we can first use a certain data set to calibrate the model. So we generated some, we use a data set to let the model generate some response. And then we add Aurora to the model. So when we turn the LoRa off, it's the model's original output. And we turn the LoRa on, we do the KR divergence for the model with the LoRa on and the LoRa off. So in that case, the model itself doesn't change, but the LoRa, and it will just get the original model's output. And the LoRa, when LoRa, the Medusa has with this LoRa width, it can just continuously and slightly change the distribution of the models with, and then learn how to predict more tokens without severely damage the model's performance. So that's the idea how we use uh this without the data cell, without the fine-tuning strategies of the original model. Yep. So basically the results for Cipher 7B, Vicuna 33B, these two are the one we don't have the recipe, so we just use that way, and seems like this can have a slightly lower acceleration rate compared to one we have the recipe, right? But they still have a significant improvement in acceleration or speed up compared to the original model. Okay, so also we have the one glimpse of the speculative decoding. So we use a Vicuna 1B, Llama 1B. These are two models we get from using a tiny llama, and Vicuna 1B is one like do soft fine tuning, supervised fine tuning. Sorry, why I always go supervised fine tuning, soft fine tuning. I don't know. And yeah, just Vicuna 1B and Llama 1B here, and indeed we can see some very interesting results. The llama 668 million, this one. Actually, this one is better for Vicuna 7B and Vicuna 13B. It achieves a better token tokens per second. We basically like speed up. Original is like this gray line, and yeah, the gamma is like how many tokens for speculated decoding models to observe. Like for example, here this one we have these three tokens. This is the best option. And use Llama 68 million. This one is the best draft model. But yeah, it's still slower than using the Medusa. No. And for Vicuna 33B, you can see we can use the Vicuna 1B. This is better, right? Also Gamma 3. Yeah, just some explorations and for adopting like whether which model we need to choose for using the speculative coding and the hyperparameters we got to choose. Basically, like analysis. This not too much to talk about here. Yeah. And also another thing is typical acceptance sampling. Uh, we try to improve the efficiency in generating diverse outputs from the language model, which means the random sampling always cut off in the middle, which means some outputs can be accepted by like lower the tolerance or lower the threshold, like can be accepted, but and doesn't significantly impair a model's generation quality. But for random sampling, I don't accept it. So we would just want to achieve the higher acceptance and make the generation faster, right? So this is a formula, and we just explain this one. Greedy sampling, we have the one token get accepted by the LLM. What we do is guessing. The guessing must matches the top one. For example, if this is the I and this is M, right? If the guessing is like I prime and even prime is here, M is here, right? It doesn't match the M, so this will be rejected. So greedy sampling is very strict, right? Guess much must matches the the gas token from either speculative decoding or parallel decoding must matches the accepted outputs, the top one results. And for the nucleus or top K sampling, it's just like it's a hard threshold. And for example, if it's I, and this M prime, etc., and the gas token is prime, is inside this, it can also be accepted. So this can be accepted if this is prime, cannot be accepted. Okay, go to next. And this one is like I, for example, if we have this, for example, the gassing is like want, and want is somewhere here. So want also will be, sorry, want will also be rejected. Want will be rejected. This will be rejected, and this will be accepted. But what if in this one? Because the threshold, you basically understand this is kind of like dynamic threshold. So it depends on like the entropy of the your output logics, and it calculates this is uh the formula. You have this epsilon and this delta, right? So yeah, just like dynamic thresholds. And try to accept more tokens, and the quality doesn't drop that a lot. So basically the same thing. Okay, we can see here we have this greedy and this random sampling. Random sampling's acceleration rate is lower than greedy. And but for scores, it's like on a benchmark. We have the GPT-4 as a judge. So they achieved a very similar scores, but for you, we changed the posterior threshold of typical sampling. And you can see here, typical sampling, when we change the threshold, make the threshold larger, the sampling acceleration rate drops, but it's still higher than gradient random sampling. And also the scores like it's just like on par with the gradient random sampling, and it has a significantly higher acceleration rate. That's the idea we use. Like we can use a typical sampling instead of using the random sampling or nucleus sampling. Yeah. So we can go to another like the paper, and the last thing I want to mention is the uh some explanation of the memory bandwidth uh button like bound. So here we have this uh so this is the calculation of each operators in the like it's a computation heavy operators, basically like linear layer and attention layers uh in the LLM. Here we just use the llama, like the llama architecture, and they have this UG gate uh up and down. So get up and down, these are linear layer, these are linear layer, this attention, and this is also a linear layer. So this is a QKB linear layer, attention, get up down. If you don't familiar with this, just check the llama architecture. input shape, output shape, complexity, space complexity, etc. Uh, yep. So we have this benchmark. So for you can see here for linear initialization, linear MLP, they're basically we just mentioned one thing, same thing. QKB MLP init, like this is a roofline model basically. So it just calculates the props and operation no intensity. So this this curve is like here, this curve, the ratio of this one divided by this one, uh, and this is a memory bandwidth. If things under like under this part, this is memory bound, and for things go to this part, the compute bound. Basically, you can interpret this figure as uh from a left side, right side. This area, this region is not approachable. So yeah, for more of like how to read the real-time model figure, you can just Google it and do Wikipedia. Just read the Wikipedia. You can see here QKV, MLP, initialization, up, gate, down, initialization. They are like in here, which they are computational bound. But for the QKPV init, this is the attention QKPV They're here, right? Which means they're sig significantly memory bandwidth bound. And for all the autoregressive operators, they're just memory bound here. So memory bound, which means we didn't fully utilize the computation. And thus we can use the speculative decoding or parallel decoding to shift. For example, we have here in this one intensity of the matrix attention matrix multiplication with batch size 16. So this is like how many candidates or how many nodes on the tree we have, right? The draft tokens we have it's just a same term draft tokens, candidates, etc. This is the original AR. We have the autoregressive for attention. They're here. The operators they're here, which means they have very low operational intensity. But if you add more candidates, they will just go to the right side, which means although they are still memory bound, but they just utilize like more operations, right? More flops because the operational intensity increased. Okay. And yeah, just go down to the next slides. Yeah, just comparison. For example, here, this is the up, gate, down, this linear layer. Still, if we don't do any optimization, just use the autoregressive, just each time decode one token, they're right here. And if we add more token, like speculative decoding, barrel decoding, it will just shift to the right. And finally, it will reach the region of computational bound instead of the memory bound. So you can just read through this one. It just explain why these models are slow during the inference and how speculative decoding or parallel decoding they can help accelerate the inference. Okay, so here this is the simulation of the acceleration rate. Basically, the one if you remember in the slides or previous section of the paper, we have this tree and then like the tree attention, sparse tree, and we use a log, like a log curve to simulate this acceleration rate. And we benchmark the speed up and normalize latency using different number of candidates tokens under circumstances like batch size 1, sequence length 10, 24 for L, llama 7B. And we can see here there's a drop after candidates tokens exceeds 64. They have this drop here. Yeah, if this just matches the experimental results. And we can use this way to if the model get larger, we can use this very simple method to estimate the Medusa's performance on a larger model. Yeah, and on different architectures, like hardware architectures. Yeah. Basically, also there are some very interesting tables you can read. Like for this one, it's like simulated speed up with batch size for Llama 7B, and if the sequence length it's like 8K, this one speed up will drop a lot, which indicates we need more uh optimizations, dedicated optimizations for long sequence instead of just pure using Medusa, right? And also it had this batch size, different batch size. If we have 64 batch size on one GPU, the speed up will be negative. Basically, it will slow down using Medusa because you have 64 batch size and you also have a lot of speculative tokens or parallel decoding tokens. The computation will just be very, very heavy for a GPU to do that. So we can consider some situation like you can use a distributed system to do the inference. Uh, and there's a lot of space for optimization beyond just purely using the Medusa. Yeah, I think basically that's all we talked about today. And thank you.